You are welcome to my lesson. As I had told you earlier, Mr. Muirori, today's lesson I would like us to look at how we convert mass of substances to moles of particles, and also how we calculate moles of particles of solutes in volumes of solutions, and finally how we calculate moles of particles in volumes of gases. In these three ways of existence of matter, calculations have to be different because the way the particles are arranged in solids and also in solutions and in gases, it is very different. Therefore, the calculations will be different. Let us start with the way we convert masses to moles of particles. And right now, I would like us to look at this magnesium piece of magnesium metal. This metal is 0.3 grams. I would like us to calculate or we count the number of atoms in this piece of metal. We want to know how many moles of atoms are in this piece of metal. To do that, we convert masses of substances to moles by dividing the mass we have by the relative formula mass. So, moles, we get it by the mass we want to convert divided by RFM. RFM is the relative formula mass. So, for example, a formula like sodium carbonate, you can see that the formula is having 2 atoms of sodium, 1 atom of carbon, and 3 atoms of oxygen. We can add up all the relative masses of those atoms to get the total. The total is what we call the relative formula mass. For example, for sodium is 23, and therefore the 2 sodiums here will be 46. And carbon, an atom of carbon has got a relative mass of 12. An oxygen atom has a relative mass of 16. The 3 atoms in the formula have a mass of 48, and the total mass in the formula is 106. I would like us to convert, or rather I would like us to work out how many moles of atoms are in this piece of metal. So what we are going to do is we are going to have the mass of this metal. We divide by the RFM. The RFM here, this is an element. So here we talk of relative atomic mass. The formula of magnesium is 24, and the relative atomic mass of magnesium is 24. So magnesium is equal to 24, and here the mass we have is equal to 0.3 grams. Therefore, the moles of the atoms in this piece of metal are 0.3 divided by the relative formula mass of magnesium, which is 24. And you now get 0.3 divided by 24, you get 0.0125 moles of atoms of magnesium. So already we have counted all the atoms inside this piece of metal. If we want, like the way you can talk of 0.5 dozen, 0.25 dozens of articles That's how now we have done. But if you want to get individual atoms in this piece of metal, since the number of moles is 0.0125, we will simply multiply that by Avogadro's constant. And 1 mole of atoms or any particles here is equal to 6.0 times 10 to the power 23 atoms. So we have 0.0125 moles. Therefore, the exact number of atoms in this piece of metal are 0.0125 multiplied by 6.0 times 10 to the power 23. These are atoms of magnesium. And how many atoms are there? So we have multiplied by 6 there. So we get the total number of atoms are 7.5 times 10 to the power 21 atoms of magnesium. So we have already counted all the atoms making this piece of metal. They are 7.5 times 10 to the power 21 atoms of magnesium. All of them, they assemble together, they are heaped together to make this ribbon. If you want it in another way, these atoms are 7, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 atoms of magnesium. You can now imagine how small atoms are, but these figures are huge numeric figures, and we don't use them in our calculation in chemistry. We simply use mole because those figures are big. We use moles, and that is how every time we want to convert a mass of substances to moles, that is how we do it. We get the mass we want to convert, we divide by the relative formula mass. Any substance in chemistry is expressed as a formula, and you only need to look at the formula. You look at the number of atoms represented in the formula. Atoms have relative atomic masses. Then you sum up all those atomic masses in the formula to get the RFM. For example, the RFM, as I said, of sodium carbonate is 106 because all the atoms represented in the formula are 106. That is not the only way we quantify substances in chemistry. Many other times in chemistry, we have substances which are in solution form. Like, for example, this is sodium hydroxide, which is in solution form. Sodium hydroxide is an ionic substance. Therefore, it exists in solid form in at room temperature. In many reactions, it will not react when it is in solid form. In most cases, we want to make it a solution. Then we do whatever kind of reaction we want so that we can get the results we want. But the question is how do we get the number of moles in a solution? Because as a solid, we have seen how we can do it, or when it is measured in mass form. But when it is measured in volume form as a solution, we need also to know how we can do it. This solution, solutions have got concentrations. we can have a solution which is dilute, therefore containing very little amount of the solute. We have other solutions which are having a lot of solute dissolved in them. Therefore, when we are calculating moles of substances in solutions, we need to consider the amount of solute dissolved there. Concentration is measured in terms of moles per liter. That is, moles per liter is an expression of how many particles are there in the solution, in a liter of that solution. The other way we measure or we express concentration of a solution is in grams per liter. And in this case, we talk of the mass of the solute that is there in a liter of that solution. Maybe we can also express it in kilograms per liter. But in chemistry, because substances, they react in terms of particles, we always like expressing our concentrations in terms of the number of moles which are there in a liter of the solution. In our question that we are trying to, in our second part, that is how to calculate the number of particles of solute in a solution, let us try to solve this question. Calculate the number of moles of sodium hydroxide in 50 centimeters cubed of 0.5 m. So the solution is here. This is 0.5 m sodium hydroxide. We would like to know how many particles are inside here in terms of moles. You see, this solution is having water, much of it is water, but we have got the sodium hydroxide particles also in the solution. We need to count them, and we count them in terms of moles. The way we count items, some items in terms of dozen and so on. So how are we going to do it? You get the volume of that solution. And in our case, the volume is 50 centimeters cubed. Then from there, you get the concentration of the solution. And the concentration in this case is 0.5 m. And I hope 0.5 more, you know what it means. It means that in 1,000 centimeters cubed, you find 0.5 moles. These are the number of particles you find of sodium hydroxide. Our business is now a smaller volume of 50 centimeters cubed. We would like to know if such a solution is looking like that. Suppose we draw out a smaller amount of solution from that liter, and we want to know how many moles are there. Already we know in 1,000 of this type of the kind of solution how many moles are there. So we just simply do simple proportions here. You say this, that a proportion of you have lather 50 centimeters cubed divide by 1,000 centimeters cubed multiplied by 0.5 moles. So that is how you do it. 50 centimeters cubed over 1,000 centimeters cubed multiplied by 0.5 moles of sodium hydroxide. And this is the amount of sodium hydroxide that is in that solution in terms of moles. And finally what we have is this is 50 times that is 250. 250, then we count the decimals, 1, 2, 3, 4. So those are the number of moles we have in this solution. They are 0.025 moles of sodium hydroxide. So those are the number of particles of sodium hydroxide inside this together with the solution. This solution is 50 centimeters cubed, and that is how we get number of moles inside a volume of a solution. You get that volume you want to know over 1,000 multiplied by the molarity of that solution. Let us now go to the next part. The next part is we want to know how many, or rather how do we calculate the number of moles in a gaseous volume. You know very well that a gaseous volume will be treated differently from a volume of a solution. So we are now tackling the other activity. So here we have a volume of carbon dioxide. This gas, I have prepared carbon dioxide, it's a colorless gas, and it is containing in this gas jar. We would like to know how many molecules, how many particles are inside this gas jar. And it is a very simple activity. So the volume here, the volume is equal to 275 centimeters cubed, and we are at room temperature. And at room temperature, as that activity is telling you that at room temperature, the molar gas volume is 24 liters. So that tells you that any 1 mole of a gas, yani 6.0 times 10 to the power 23 particles of a gas at room temperature, they occupy 24 liters. Therefore, then what you'll say is this, that that is 24 liters of the gas. You find how many molecules or how many moles of the gas. You find 1 mole of any gas, that is maybe here CO2. You want to know our volume, that is 275 centimeters cubed. You want to know how many moles are there. Just again, simple proportions. This is 275 centimeters cubed divided by 24 liters. You have also to express it in terms of centimeters cubed so that the units can cancel. This is 24,000 centimeters cubed. That is when you convert 24 liters to centimeter cube, multiply by 1 mole. This one now you get 275 divided by 24,000, you get multiply by 1, you get 0. You get 0.01146 moles of CO2. These are the number of particles of CO2. These are the number of particles of CO2 containing in this gas jar. If you want to get individual particles of CO2, individual molecules, you multiply by 6.0 times 10 to the power 23, because a mole of particles is equal to that Avogadro number. We call it Avogadro's number. So that gas jar is therefore containing those number of moles of CO2. So finally, that is the end of my lesson, and that's how we convert masses of substances to moles, volumes of solutions to moles, and volumes of gases to moles.